So we've got this idea of atoms. And then J.J. Thomson studied cathode ray tubes. So what a cathode ray tube is a partially evacuated glass tube. So there's some gas in here, but not very much. And they put a high voltage. There's a metal end at each end. This is called the cathode, that's called the anode. They put a high voltage across there, and that causes what looks like a beam of light to travel from one end to the other, and that's called a cathode ray. The cathode ray goes from the cathode to the anode, and that's why it's called a cathode ray. Otherwise, they might call it an anode ray. That's cathode ray. And this is actually the basis, the idea behind a CRT television. Do you remember those? They kind of had a curved screen, really deep. Those were cathode ray tubes. And they used this technique to display pictures on the front of that tube. So he observed these cathode rays and realized that it was a stream of particles, and they had the following properties. They traveled in straight lines. They were independent of the composition of the material from which they originated. So you could make the cathode, the metal end of that tube, out of different metals, but the cathode rays behaved exactly the same way, regardless. He also found that they had a negative electrical charge. Electrical charge is a fundamental property of some particles. It results in attractive and repulsive forces. Electrical charge is a little bit like magnetism. And so this is what we need to understand about electrical charge. A positive and a negative electrical charge will attract each other, just like the negative and, the positive, no. Back up. The north and south poles of magnets will attract each other, right? And like charges, positive and positive or negative and negative will repel each other. Just like if you take two magnets, you put them together one way, they stick together. You turn one of them around, so you've got north pole to north pole, and you can't push them together because they're going to repel each other. So that's what electrical charge does. So these particles had a negative electrical charge, and that's why they went from the negative end of this tube to the positive end. They were repelled by that negative electrode, and they were attracted to the positive electrode. So he made a slightly different cathode ray tube. This is a little bit more like what a television would be, except you'd have kind of a squarish end here. But you can take that beam of charged particles and you can cause them to be deflected. You can deflect them using electric fields. You can deflect them using magnetic fields. And so by looking at the amount of deflection and the strength of the electric and magnetic fields, he was able to measure the charge to mass ratio of the particles. He couldn't measure the charge of them, he couldn't measure the mass of them, but he could measure the ratio of charge to mass. And he found that that was negative 1.76 times 10 to the third coulombs per gram of particles. So that implied that the cathode ray particle was much lighter than an atom, even the smallest atom, hydrogen, about 2,000 times lighter. And this was incredible. Remember, they believed that an atom was indestructible, basically a solid sphere, just a solid piece of, we don't know what, but it's solid like a Lego brick. There's no moving parts inside of a Lego brick, right? There aren't. But they had chipped pieces off of atoms. That's what this suggested. These particles in the cathode ray, they had charge, and they were far smaller than an atom. They have to be something, right? What he had discovered was electrons. Electrons are negatively charged low-mass particles that are present in all atoms. All atoms have electrons. That's why changing the material of the cathode didn't change the cathode rays. Because whatever you put in there, it's got electrons, and it was the electrons that are moving. It's actually electric current that was flowing through the gas. So this was the first evidence that all elements are formed from the same particles. They actually have something inside of them. 1909, an American physicist, Robert Millikan, did an experiment we call Millikan's oil drop experiment. So he's got this chamber here with 2 levels, and in this upper level he takes an atomizer and makes a fine mist of oil particles. This plate here, the second floor, has a small hole in it and a positive charge on it. Some of these particles will fall through the hole. Gravity causes them to fall down. Down here we have a negatively charged plate. Neutral oil particles will just fall. They'll fall based on the force of gravity and how big they are, how much they weigh. And here we have a viewing microscope, so you can look through here, and a light source, because you can't see things in the dark. So he could watch the particles fall, and he could figure out how much they weighed by how fast they were falling. And then he took and shot some ionizing radiation in here and basically blasted these so that they would have a charge on them. They became negatively charged, and then they would be repelled by the bottom plate and attracted to the top plate. And by adjusting the charge on those plates, you could use that electric force to oppose the force of gravity and get particles to just hang in midair. So now that I've given you a basic explanation, let's watch this YouTube video explanation.
In a series of experiments carried out between 1908 and 1917, R.A. Millikan succeeded in measuring the charge of the electron with great precision. In his experiment, a fine mist of oil was sprayed into the upper chamber with an atomizer. Some of the tiny oil droplets fell through the hole in the upper floor, and Millikan was able to determine the mass of an oil drop from its terminal velocity. Next, Millikan used an X-ray source to ionize gas molecules in the chamber. Electrons from this ionization process adhered to the oil droplets. The oil droplets now carry a negative charge. The negatively charged oil droplets can be halted by adjusting the voltage across the 2 plates. As the voltage across the plates is increased, the velocity of the oil drops slows. As the voltage is increased further, some drops will begin to move upward toward the positive plate. If the voltage is set just right, an oil drop can be suspended. When an oil drop is suspended, its weight, mass times acceleration due to gravity, is exactly counterbalanced by the electric force applied. The electric force applied equals the applied electric field, E, times the charge on the drop, Q. Since the mass of the oil drop, the acceleration due to gravity, and the applied electric field are known, Millikan could solve for Q, which is the charge on the drop. Millikan found that droplets had different charges, but each was a whole number multiple of a smaller charge, equal to negative 1.60 times 10 to the negative 19th coulombs. Millikan concluded that this was the fundamental unit of charge, the charge of an electron. From the charge of an electron and the charge-to-mass ratio of an electron determined by Thomson using a cathode ray tube, Millikan was able to calculate the mass of an electron. The mass of an electron, 9.10 times 10 to the negative 28th grams, is an exceedingly small mass.
What I think is really cool about these experiments in the past is I think it illustrates what is fascinating to many scientists about science is, you know, we're not just trying to find the length of the bench top. You could just take a ruler and measure that. We're trying to figure out things that can't be seen or measured. And so it's like a puzzle. And you have to figure out, well, how could we measure this? If we knew this, could we find out this? And so here, even though you can't measure the mass, or Dalton couldn't measure the mass, Millikan was able to measure the mass. And because Dalton had the mass to charge ratio, then we can get the charge. So he looked at the strength of the electric field, needed to stop the drops from falling, and figured out the masses, and then he was able to find the charge on each drop. So the charge on each drop, he found out, because each drop didn't necessarily have the same charge. They had some different charges, but he found that they were all multiples of minus 1.96 times 10 to the minus 19. So if you had 2 electrons, it would be twice that. If you had 3 electrons, it would be 3 times that. And so he was able to figure out the charge on the electron. If you take the charge on the electron and the mass to charge ratio, you can figure out the mass of the electron, which is 9.1 times 10 to the minus 28 grams. Yes?
Do you just know that formula right
You do not. You do not need to do this calculation. Not on a test anyway. There could be a question like on a homework problem or in a worksheet that requires you to do something like this. And this is basically unit analysis, dimensional analysis. Here you have grams and coulombs related to each other. Here you have coulombs, you want gram, and so we just use this as a conversion factor.